Hello, the purpose of this video is to talk about two of the major uses of calculus, or some of the more practical uses of calculus. Perhaps this might be the time in your mathematical education where you finally see when people might use something. Even here, these are oversimplified models, but nonetheless. So anyway, the two things that I'm going to demonstrate are how to find the length of a curve. So we know how to use calculus to find the area under a curve, but what about finding the length of a curve? So what it says is an algorithm here that says the length is the integral from a to b of the square root of 1 plus or minus the derivative of the function you're finding the length of, squared, dx. So remember, y is going to be the function. For example, here I have the Fox River from Appleton to Green Bay. I superimposed this map on a grid, and as you can see, the image for the scale for 2 miles was given to me on the map. And so then what I did is I created a tick mark or scale so that 2 miles is represented by each tick mark. So right here, for example, from Appleton to Little Chute is approximately 4 miles across, and there's about 3/4 of a mile up to get from those two places. So again, you have to make sure that the scale translates from whatever scale you create on your image to real miles so that we can get an actual distance or an actual length. Then what I was able to do is actually plot points along the river every 2 miles. Every 2 miles I put a point, and then I can go through and using a ruler or using Desmos, I could actually find the vertical positions every 2 miles along the river. That's the data collection piece. And then what I'm able to do is create a regression equation, and what a regression equation will do is give you a curve of best fit. So you can see this blue curve is sort of modeling the Fox River. It's not going to be perfect because you can see the Fox River deviates from the curve quite a bit over here, but for every curve deviation above my function, there's another deviation below the function. So we should presume that a lot of that stuff is going to sort of cancel itself out. Again, this is just going to give us an estimate anyway. So I found that function using regressions from the TI calculator. You can enter the data into the TI calculator and do a polynomial regression. In this case, it's a Kintic regression to get a 5th degree polynomial. But we can also get this on Desmos, which is demonstrated in an earlier video. Either way, once we find the equation that models this particular function or curve that we found, once we found that equation, we can simply put that into the graphing calculator. First we can find the derivative. We call that y2 is going to be the derivative of y1 with respect to x. And then I can enter in the algorithm for my function. See, the function says the square root of 1 plus the derivative squared. And we're going to integrate from a to b, in this case from 0 to, what is this, 2, 4, 6, 8, 10, 12, 14, 16, 18 or so. So I'm going to integrate from 0 to 18.2 and using this. Actually, I just did to 18 apparently. So basically, I put in the function that I'm going to integrate, I graph the function that I'm going to integrate, and then I find its area under that particular new function's curve, and that's going to represent the length of that specific curve. So according to my work, I found the Fox River from Appleton to Green Bay to be about 25 miles in length, 25.3. We'll go to Wolfram Alpha, and I put in the distance from Green Bay to Appleton, and that turned out to be 24.71. Now that's the distance from Green Bay to Appleton as the crow flies, or maybe as the highway goes, and this is the length of the Fox River. So I don't know that they're exactly accurate, but I do know that my river is estimated to be around 25 miles, and the distance between those two cities is said to be around 25 miles. So I feel really good about this particular estimate. The other thing we can do with calculus is we can take a curve in 2 dimensions, like this curve, and simulate what would happen if we spun that curve around the x-axis. We could even spin around the y-axis. And what that does is it simulates 3-dimensional shapes that will be symmetrical. They have sort of a rotational symmetry. It would be like using a lathe to carve something like a baseball bat or a vase or something like that. The algorithm works out based off of the area of a circle. The notion is that if you have a function value, so for example, here's x, here's f of x, f of a in this case represents what could be the radius of a disk. if we spin this radius around the x-axis, it produces somewhere a disk like that. So in 3 dimensions we now have a circle, and we can find the area of that circle by using pi r squared. Pi r squared gives me the area of a circle, but the radius of this circle is in fact the length f of a. So the function tells me how long the radius of this circle is going to be. If I square the length of that function at f of a, that will be the square of the radius, multiply that by pi, and I've now represented the area. Let's take that one step further. What if we had the same values for f of a and f of b, and they're so many units apart? That can create a 3-dimensional object that looks a lot like, well, a cylinder. So now I can find the volume of this cylinder using the volume algorithm, which is the same as the area algorithm, times the height of the cylinder. So pi r squared gives me the area of the top and bottom of the circle, and then the height is the distance between a and b. So if I multiply pi times the function squared, and then multiply that by b minus a to get the distance between a and b, then I will have the volume of that particular shape. We're going to take that one step further and look at what happens when the function is curved. See, if we have a function being curved, instead of creating one giant cylinder, what we're going to do is to simulate a bunch of little tiny cylinders, little tiny disks along the way. So, to get the volume, we're going to take pi times the radius of each of those disks squared times the height of each of those disks. So each disk is going to be small, but we're going to make it get smaller and smaller and smaller. So let the height of the disks get infinitely small, and then the sum of the volumes will become an integral of the volumes. So this right here is the algorithm for volume of revolution. If you can find the function for a curve, like y equals f of x right here, then you square that function, multiply by pi, and integrate from top to bottom, and you will have now the volume. You can see here, if you pause this screen, you will see how that process is done for the parabola y equals x squared. From 0 to 5, we can take that shape and spin it around and create this little cone type hat, and we can do so very simply, and now 625 times pi will represent the volume of a container that looks like that. All of this work can be done on the calculator. Again, I would encourage you to, you could either pause the screen and try to read this, although it's a little blurry. The other option would be to get the notes from your teacher. So, one of the things we're going to do then is to use that to find the volume of 3-dimensional objects like this. So more to come. But anyway, if you want to know how to find the volume of revolution, the algorithm is right here. Again, we integrate from a to b of pi times the function that represents our curve squared dx, and that'll work every time. If we want to find the length of a geometric or geographical shape, we use this algorithm. We're going to integrate from a to b, the square root of the derivative of a function squared plus 1. Okay, and again, there's reasons for all of this, but I hope you find that helpful. Thanks for watching.